Thank you. Sorry. So good morning, everyone. Thank you for coming today, and thank you HITB for having me. The topic for my talk today is understanding the protected view sandbox. A little bit about myself. My first name is Yong Chuan, and you can call me Yong for short. And I am a security researcher with NWR Labs since it started in Singapore in 2014. Personally, I am interested in vulnerability research, in particular those that are in Windows applications, and also reverse engineering to find the root cause of the bugs, just to see how that happens, and to make fun of the developers' mistakes. But anyway, along this process, I may develop fuzzers or other tools, and I also like source code reviews. Occasionally, I also analyze malware to understand its behavior and to identify some IOCs, sometimes to do other things other than vulnerability research, and other times to support the company's other business. So here's the outline for today's talk. I will begin with an introduction on the protected view sandbox, and also the motivation and goals behind revisiting this research. And in the next section, I will talk about the sandbox internals, which will include the initialization process, the app container capabilities, and finally, the architecture of the sandbox. From the architecture, I will then focus on the IPC mechanism. And in this section, I will talk about the internal objects that the broker uses to track and differentiate each protected view files that it has opened. This is followed by a few words on the general format of the IPC messages before we take a closer look at a particular Windows code that affects two of these messages. And finally, of course, it ends with the conclusion. And now let's begin. So just to have a baseline, let's set the definition for sandbox. Our reliable Wikipedia defines it as a security mechanism for separating running programs. It typically provides a tightly controlled set of resources for guest programs to run in. It is implemented by executing the software in a restricted OS environment and therefore controlling the resources that the process may use. So in other words, when you put an application in a sandbox, it would be putting it in an imaginary box with just the minimum OS resources that it requires to function. In practice, this restriction may break some of the application's functionalities. And therefore, typically, sandboxers would need to request the broker to perform certain tasks for them. And that's why we have the IPC in general. The PV sandbox is a feature that is introduced since Office 2010, but unlike most other sandboxes, the protected view is not used to render all the files. Instead, it is used only for files that Microsoft defines as untrusted. And these largely cover files that originate from the internet, such as those that you download, or when you open it directly as an Outlook attachment. So the first telltale sign that the file is open in a sandbox is in the document title. And then the next obvious sign is the golden bar. And then if you scroll along, you can only see a text view mode. So in this sense, all other unnecessary features for the viewing are disabled. In this and the next slide, we will try to deduce why Microsoft decides to implement the protected view sandbox. Here we see the number of vulnerabilities that affects Microsoft Office for the last 7 years. From 2010 to 2014, the number is actually less than 15 for each year. This is a very low figure considering the huge and complex code base that the Office is built on, and also the popularity of this set of applications. But in 2015 and 2016, there's a sharp increase in the numbers, with Google Project Zero contributing a large portion with their Office fuzzing. And this figure also includes the vulnerabilities in the kernel graphics components, like the GDI, GDI+, and fonts, that could be triggered from the Office. So this type of vulnerabilities also add to these numbers in these 2 years. If we zoom into these 2 years, we differentiate the memory corruption vulnerabilities from the other types. And it turns out that about 70 and 55% of these vulnerabilities are actually memory corruption for which the protected view sandbox is effective against. So if you think in terms of the absolute numbers, this sandbox actually doesn't mitigate a lot of them. But if you consider that The Office application is a very popular enterprise software whereby one successful exploitation results in a very far greater impact. So what I think is that the decision by Microsoft to invest in implementing this sandbox is based on impact rather than the number of vulnerabilities in this software. For me, the motivation for this project arises because of this year's Point to Own. In the new enterprise applications category, Adobe Reader, MS Word, PowerPoint, and Excel are included as targets with their sandbox enabled. So I became interested not because I want to take part in the competition, but to try and see how other researchers would try to break out of the sandbox. And subsequently, I began to wonder whether the sandbox has changed or if I had missed out anything in the earlier research. So the goal of this short project is just to check if there's any changes made compared to the one that I did for Office 2013. The next obvious goal is to try and break it and have fun in the process. The analysis is based on this particular version for Word. So moving on this section, I will talk about the sandbox internals, which will include the initialization process and also the architecture. This process actually starts in the 2CA E9E routine in MSO.dll. This routine takes 3 arguments, for which the third one actually affects certain fields in a local structure variable. This local variable contains information on how the sandbox should be started, and it is 30 hex bytes large. Interestingly, by default, many of the fields are unaffected, although there's different code branches to them. So at the moment, I'm not sure why, how they could be influenced to take the other branches. Yeah, but it could be some settings. So this is the complete semantics of the startup option structure. The first is the sandbox ID, which is generated randomly for a possible 16,000 values. Next is the capabilities that are to be added, and by default, only the MS Office seat is added, while the rest are not. The next set of fields set the job restrictions on the sandbox, and these are the active process limit, completion port, job memory limit, and also the time limit. The next 4 bytes determine whether to start the sandbox in a separate desktop, and if it is, then it adds more UI restrictions and also the logon user. And finally, the bytes at offset 2D and 2E are interesting because they affect fields to another object, shown as ESI here. The ESI object will eventually be used to determine the type of sandbox that the protected view will use. So the check use AC field by default is false, but if it is true, then the broker checks an undocumented registry key. The local machine software Microsoft Office 16 common security use app container registry key to determine whether the app container sandbox should be used or not. If it is, then it also checks whether the OS supports this app container feature by getting the prop address of this particular API. So the whole process starts with the creation of the sandbox ID, which is appended to form the unique sandbox name. Next, the job restrictions are set, with those in bold set by default. And then the capability seats are added after checking that the OS supports app container. And then the directory, and if necessary, a separate desktop are created. And next, the broker creates and connects to the IPC pipe. The pipe is created with the sandbox name as the substrings, which in turn contains the sandbox ID. So in this sense, it makes the pipe name unique. The next thing to note is that the buffer size are limited to 2000 hex, which correlates to the maximum size of one IPC message. And finally, the sandbox process is ready to be started in 3 possible modes. In the first mode, in the absence of the use app container registry key, the sandbox is created. The process is created in whatever sandbox that the OS can support. So in other words, in Win 7, it's created as a low integrity sandbox, while in Win 8 and above, it is created as app container. The second mode is intended for Winnet and above, and it allows the user, for whatever reasons, to use the low integrity sandbox instead of the app container one by specifying the use app container registry key. And in the last mode, if both the use app container key and ESI plus 81 bytes are set, then effectively the protected view mode is disabled. Now, the app container is largely based on capabilities, and this in turn defines the OS resources that the sandbox can access. In the initialization, we saw that the MS Office set is the only capability added to the protected view. Typical well-known capabilities are defined in either winnt.h or the capability mappings registry key. But in this case, this MS Office capability is not documented or defined publicly. So in terms of resources, I am basically interested in these three types. The files access, because if the app container has file access to some trusted locations, like the Office template directories, then I could potentially load myself unsandbox the next time Winword opens if I can copy my own document to that directory. And then networking, because there might have been some obscure protocol handling issues that would be handled by the broker instead if the request was made. And registry keys for pretty much the same reasons for these file access. And these are the results. So the MS Office capability has no files and networking access at all. And it is not surprising because otherwise it would have overlapped with the internet-related capabilities. So it appears that this capability is meant for key read access to the MS Office registry keys, which is actually reasonable because these are outside the app container default restrictions. So among the Office registry keys, the trusted location is the most interesting because any documents run from that location are assumed to be trusted and therefore not sandboxed. So if you could somehow write your path to that registry key, then potentially you could start yourself unsandbox also. So in this last slide of the section, this shows the diagram of the protected view architecture. So this diagram is a lot more simple than other sandboxes like the Edge, Chrome, or even Adobe Reader. And it is hardly surprising given that this feature is intended to show only a text view of the files, unlike these other sandboxes where you would expect full application functionalities. So at first glance, the immediate thought is that the attack surface for the PV sandbox escape are very much decreased because there are only two higher privilege components, the broker and the kernel. But although this is true, we should also consider the security of each surface by itself. So the kernel surface by itself is actually a very large surface. And furthermore, Win32k filtering is not enabled for MS Office yet. So this chart here shows that from 2001 to 2016, more than half of the vulnerabilities are attributed to Win32k, which potentially could be caught from the sandbox with system calls. So by targeting this surface, attacker would have a higher chance of escaping from the PV sandbox like it was from Edge sandbox 2 or 3 years ago, or maybe even now. Now in the next session, I will talk about the less attractive surface, the IPC mechanism. So I will first begin with the internal IPC objects that the broker use, followed by the general format, and finally a quirk in the file I/O APIs that the developers fail to consider during implementation. This is an overview of the internal objects that the broker uses. This starts with the track manager object. This object holds references to the IPC send receive, PV startup, and PV manager objects. The IPC send receive describes the status of the name pipe and also the buffers to read or write from. The PV startup contains information from the initialization process, like the sandbox ID and etc. The PV manager does not do much except acting like a proxy to the PV tracker object. In protected view, all untrusted files are rendered in the same sandbox process, and therefore the broker needs to be able to maintain a state and track each file independently. So this actually starts from the PV tracker, whereby an overview of the sandboxing state is maintained. This includes the number of untrusted files that are currently or have been opened in the current broker session, shown by the PV file count, and all untrusted files are individually represented in an array of PV file objects pointed to by the array. In this dynamic array, each PV file can be free or busy, depending if the corresponding file is open or closed. And finally, each PV file points to a MSO message and www message objects, which should then store information about each individual IPC messages. So this is a close-up of these objects. And then this is another close-up of the PV file object. It actually describes each sandbox file like the file name. And the field to highlight here is the view ID field. It is important because it's used by many IPC messages to indicate whether the particular sandbox to indicate the sandbox file that the message is intended for. So when the broker receives this particular view ID, it would then search for the corresponding PV file in the array. So in general, both the MSO message and the www message contain fields that are referenced directly by the respective IPC message. I broadly classify these messages into two groups, depending on whether these are common or specific to WinWord, PowerPoint, and Excel. So the group of messages that are common to these three applications are all serviced in MSO.dll and has a 16 bytes header. The other group that are not common are serviced respectively in www.dll, excel.exe, and ppcore.dll, and this will have a 20 bytes header. So here's a more detailed view of the format. So broadly speaking, each message will consist of a header and a body, which in some cases is optional. The PV-based header format refers to those that are serviced in MSO.dll, and the common fields in these two groups are the message tag, which identify the message, the message ID, which would pair the IPC requests and responses, and also the size, which will have a maximum value of 2000. And this actually correlates to the pipe buffer. So in turn, this will mean that one single read of the pipe would actually be one IPC message. So in total, there are 23 PV-based messages ranging from 001,000 to 161,000. For most of the messages, there is a sanity check on the format, and values are done, and these are done in the pink blocks before they are eventually serviced in the purple blocks. For the PV-specific message, these numbers are different for WinWord, where there are 15, PowerPoint when there are 17, and Excel when there's also 17. So the sanity checks will include things like whether the size is correct by comparing the message size field with the total number of bytes received. Or if the messages have a fixed message size, then they will compare it with a constant value. It also updates any string pointers. So for example, for fields that are of type wstring, there's actually a format like the pointer, length, and the character arrays. So when the broker first receives the message, the pointer is actually a heap address in the sandbox. So during the sanity checks, the broker actually updates these pointer values. And you also check whether the string length doesn't go beyond the end of the message buffer. So as I reverse engineer the IPC messages, it appears that developers are not too familiar with the file I/O functions. If you look at MSDN, it will mention that the file I/O functions in Windows API convert forward slash to backward slashes as part of converting the name to an NT style name. So among these IPC messages, the 051,000 and 0C1000 contain fields that refers to file names. These files are meant to be found in the app container directory because the broker would prepend the app container directory to the names. So the broker would try to prevent directory traversal out by ensuring that there's no backslash in the name. But they forgot to check for the forward slash as well, and therefore directory traversal is still possible. The format of the 051,000 message is shown here. The file name that's included in this message actually refers to the temp file that Office typically creates for backup or for performance reasons. Typically, the 051,000 is one of the first few messages that are sent after the sandbox is started. And since there's no reason that the temp file would change, subsequent 051,000 messages are to be ignored if the broker receives them. So if the first 051,000 message has such a temp file name, then this will actually pass the sanity and backward slashes check. And the broker would eventually create file with this temp file name. And here we see that the file handler is successfully created. This actually refers to a file on the desktop. And after this, the file may eventually be deleted if certain criteria are met. Next, we'll look at a 0C1000 message, which is actually an error reporting request. In a typical scenario, the application process would start Dr. Watson by itself and then passes the exception information like the 14 EIP directly to Dr. Watson. But in this case, because the protected view is restricted from creating new processes, therefore, the sandbox will send this message to the broker as a proxy so that the broker will start Dr. Watson on the sandbox. And because that's the exception information, the amount of information to be passed to Dr. Watson is more than 2,000. So that's why there's a new shared memory created by the sandbox to pass to the broker, and this will in turn be copied to the Dr. Watson by another shared memory. Anyway, the WER file name here refers to an additional file that will be uploaded to the WER server in a subsequent stage. So here's an overview of what's going on in the Windows error reporting. When the 0C1000 message is sent, the WER file name set as this white string. The broker will actually start Dr. Watson, and this would present the user with 3 options. If the check online for a solution option is chosen, then Dr. Watson actually sent an XML file containing crash information like the OS and application versions, exception information, and other related files to this server. By default, this server is pointed to watson.microsoft.com, but in an enterprise setting, it is possible to change this server with the configure corporate Windows error reporting GPO. So after looking through this XML, the server may decide that this error needs closer investigations, and therefore the server can request more files from Dr. Watson. Now the user is again prompted for permission to send these files, which should include this is my file.txt in desktop, and if allowed, then these are compressed and sent as a .cat package. And finally, the .txt would then be deleted by Dr. Watson. So now for the conclusion. The protected view is actually has a very simple architecture because it actually does not have to provide the application's full functionalities. This is very much different from other sandboxes. And in this aspect, besides containing the initial RCE, it may actually reduce the attack surface for the initial RCE as well. So this actually is very different from the other sandboxes. In evaluating the IPC attack surface, the small number and relatively straightforward format of each messages actually reduces the likelihood of bugs. Yep. So if I compare the protected view for Office 2013 and 16, there's actually some new and some obsolete IPC messages, even though the number is still not high. So if you're interested in this, you can always check for new additions. So at this point, I might talk, and we'll be happy to take any questions. Thank you.
Somebody got questions? Yes. Yep.
Hi. Thanks for the talk, by the way. Did you look at any like object issues, any local issues that may be around, such as object squatting, or what about the name pipe? You also mentioned it creates a name pipe.
So the name pipe, there's actually there will be 16,000 possible names because it's limited by the Sandbox ID, right? So I didn't actually enumerate all and then see what happens, but if you can't create a name pipe, then the Sandbox just doesn't start. So yeah.
Okay, so if there's one created beforehand, it just wouldn't start?
Yeah.
Okay, just wondering. Thanks.
More questions? No? Okay, then thanks, Yong Chuan.
Thank you.